And now, electricity, section 5. Yay, alternating current. Hopefully by now you're a reasonable expert, relative expert on direct current. Now we're going to dive into alternating current since so many aircraft have AC or alternating current circuits. Alternating current means that the electrons are traveling in one direction and then traveling in another direction, and they stop in the middle. So if you had a wire, if you looked on the inside of a wire, and you could slow it down, because remember, electrons are traveling essentially at the speed of light. Electrons are going to travel in this direction, and then they're going to stop. Then they're going to turn. They're going to stop, and it's instantaneous. Then they're going to go in this direction, then they're going to stop. Then they're going to go in this direction, then they're going to stop. Then they're going to go in this direction, then they're going to stop. So at any given moment, most of the time, there's electrons moving, so when these electrons go past, we can use that energy. If we drew a diagram of what was actually going on, we'd have time. And let's do amps. Time versus amps, which start out at 0, and go up, down, and up again. And this height in here is quantity. So what you see black in here, that's what you're going to need to draw for the test, time versus amps. And a nice sine wave here, that's what DFM stands, draw for memory. This height right in here, this is quantity. And if we labeled it 0 here, and plus here, and minus here, this plus and minus is not the polarity of the electrons. They're all negatively charged. It's just telling you the direction. So this area right in here, electrons are going in one direction through a wire. And this area down in here means the electrons are going in the opposite direction. And then, of course, right at the beginning and right halfway through, no electrons are flowing. So they flow, and then they stop. They flow in the opposite direction, then they stop. And they keep going back and forth, back and forth. And in the case of aircraft, you notice I've got an old school gauge here. You notice right here in the middle, it says 400. That's right in the middle of the green arc, because on aircraft, the correct frequency of an aircraft alternating current circuit is 400 hertz, just like the rental car spelling, or CPS is cycles per second. They both mean the same thing. So we're essentially going to get 400 sine waves per second, or the length of time to get one sine wave, or the period, is 1/400th of a second. Where do you find this alternating current as powering the majority of the systems on the aircraft? That is, what's the primary power system? What aircraft have primarily alternating current? Well, instead of small turboprops, small turbine helicopters, and small business jets, we have large turbine helicopters, large turboprops, and large business jets, and then on top of that, transport category jets like a 737, a Boeing Airbus A320. That would be a couple of examples of transport category jets. When you fly these machines, you're going to need to understand alternating current, which is the purpose of this chapter here. Generators, got to have an alternating current generator. Here's a picture of one. And I'll show you some more pictures later. Purpose, you'll notice the purpose and the function here of AC generators are identical to that of DC generators and DC alternators. Why are they on the aircraft? To provide large amounts of electrical power. And how do they do their job? By being an energy conversion device. Oh no, Mr. Bill, another energy conversion device. There it is, converts kinetic energy or rotating energy into electrical energy. And of course, to have electrical energy, we need volts and we need amps. So I have some old school alternating current volts and amps, voltmeters and ammeters. And the schematic symbol for an AC generator is that sine wave. So there we go. So there's an AC generator. Now, you can try drawing this if you want to. But I'm not going to ask that you draw this on the test, and I'm not going to give you this schematic. I'm not going to give you this schematic on the test. But here's a three-phase AC generator. It's got three phases. We'll get to what that means here shortly. It's alternating current, and it's a generator. Wow, remember the word generator, guess what that means? It means it's got a permanent magnet. So the core, we'll try a different color here. The core here is a permanent magnet. Has high retentivity. Has a lot of residual magnetism. So that means it's got lines of flux here, right here, just like a AC generator or a DC generator or DC alternator. We have the field winding we're going to run amps through it and get lines of flux. Now you see that there's this dotted line. This dotted line is the part that's rotating in a three-phase AC generator. This is the part that gets spun. The part of the purpose of having a brushless AC generator is so that at high altitudes where there's no air or not much air inside the generator, air actually is a reasonable insulator. If there's less air at high altitude, electrons tend to jump around inside. So having brushes may be a bad thing, so we're actually going to get rid of those brushes. In any case, let's see what color do I want now. This field is going to stay stationary, but these output windings, of course we're used to output windings, these output windings are getting spun around and around. Essentially, it doesn't show it very well, but this field is poking into here, and these output windings are spinning around. And if this has a north pole and a south pole, when the north pole comes by, it pushes electrons in one direction. When that south pole comes around, it's going to push electrons in the opposite direction. So we're going to be getting in here, we're going to be getting alternating current, but just like in a DC alternator, we're going to pump this alternating current through diodes. So one side, we'll essentially rectify it. We'll turn it in from AC into DC. So current flow is going to come out here. Can't go against or can't go with the arrows. Electrons are always going to go against the arrows. So we're going to get direct current. So amps are always going to go through this field in one direction. So one side of here will always be north, one side will always be south. But of course, if we run amps through a wire, we get lines of flux. Now, remember, this whole thing inside of the dotted line is rotating, and these lines of flux are crossing these three output windings over here. We actually have two sets of output windings. But you'll notice on the output windings, there's no rectifier. There's no set of diodes. So we're actually going to get, as a pole comes past here, north comes past here, we'll get electron flow in one direction. As the south pole comes past, we'll get electron flow in the opposite direction. So we're going to get alternating current, and we're actually going to get three phases of it. There's three output windings. Here's one, here's another one, here's another one. So we're actually going to get three phases of it, or three outputs. But you'll notice that there is 120 degrees between each of these output windings. So what's going to happen is that these alternating current phases coming off of it are going to be 120 degrees out of phase. So this one may be like this, and let's see if that's 100 there. So the next one's going to be off by 120 degrees. So this right there, that right there will be 120. And then if we go another 120, let's go in the opposite direction. There we go. So this distance right here, or this angular difference right here, is going to be 120 degrees. And you're going, wow, Mr. Johnson, I remember that inductive reactance and capacitive reactance. If the volts and the amps are out of phase, it's going to mess things up. And you would be absolutely correct. But these three outputs here, these three alternating current outputs coming from these three outputs, output windings, are kept in separate wires, separate bus bars. So we never have this 120 degrees being out of phase, so we don't have to worry about XC and XL between the different phases. There's another picture of an AC generator. And of course, if you have a primarily alternating current power system, you want to have an alternating current generator. So The 4 type of aircraft that have alternating current as primary power systems also have alternating current generators, large turboprops, large turbine helicopters, large business jets, and transport category jets. Just like a DC generator or alternator, it takes horsepower from the engine. That makes sense. It's an energy conversion device. We need lines of flux crossing conductors for electromagnetic induction, a variable electromagnet so we control the amp output. Wow. So there's a whole lot of similarities between DC generators, alternators versus AC generators. There are a few differences. Oh wait, here's another one. Same thing as a DC generator. It's self-exciting because the core is a permanent magnet. So that's great. That means we don't have to pump electricity through the field winding to get this thing to work. We can get it to start working even without battery power. Of course, it produces alternating current, and it produces 3 different phases of it, essentially 3 different alternating currents. And the voltage is a lot higher than DC generators and alternators. They're rated at 120/208 volts, and this is typically what you would look at if you looked at the data plate on a 3-phase AC generator. They pretty much are always going to say 3-phase AC, 120 volts/208 volts, alternating current, and 400 hertz, because that's what it's going to put out. Now, constant speed drive. Before, all we had to worry about with the DC generator or DC alternator was the amp output to maintain a constant voltage. But now the frequency of how fast the frequency of this this AC generator is based on how fast it spins. The faster we spin it, the more sine waves per second we're going to get. So we need to keep it spinning at a steady speed. We're going to do this with the constant speed drive. Let's see, I'll just draw pictures here. Here we have a jet engine. I don't like that jet engine. Let's say we have a jet engine. And we got compressor blades. Air's going to come in the intake. And we've got a spool or a shaft coming back to some turbine blades and a combustion chamber in here. And this shaft in the middle here has a lot of power on it. What we can do is take power off of it on another shaft, and we can call this box here with a lot of gears in it the accessory section. I love accessory because it has 2 C's and 2 S's. This accessory section, it's just like the back of a Cessna 172 engine where you bolt the magnetos and you run the vacuum pump, or on a car where you run the fan belt to run the alternator and run the air conditioner. There's something on the engine where you can get power out of it, not just to drive the aircraft or the car. So the power comes out and it's going to come into a shaft and it's going to drive a constant speed drive. And the constant speed drive is going to drive the AC generator. So during normal operation, we're going to take power off of the engine to run the accessory section. The accessory section is going to drive the constant speed drive, and the constant speed drive is going to run the AC generator. If we want it to have 400 hertz or 400 cycles per second, the only way we can get it to maintain this frequency is to maintain the RPM of this generator at that one specific speed that will produce 400 hertz. And you don't need to write this number down, but it's typically 6,000 RPMs. So this constant speed drive has to accept a variable RPM from the engine, because we're going to move the throttle back and forth and the engine's going to slow down and speed up. But the constant speed drive has to be able to receive that variable RPM but produce or give to the AC generator a constant RPM, hence the phrase constant speed drive. And it effectively does this. Let's see. I'm going to make this drawing a little bigger here. Here's the accessory section. Power's going to come down, power's going to go out, and we're going to have the constant speed drive, and it's going to drive this AC generator. They're not really that big compared to the engine. Drawn, not to scale. Okay, so the constant speed drive, the power is going to come in. Power is going to come in, and it's going to drive a hydraulic pump. Hydraulic pump is going to send fluid to a hydraulic motor. And on that hydraulic motor is going to be a governor. Works essentially the same as the propeller governor on a PA-44 or any other airplane that has a constant speed propeller. In that case, it varies propeller pitch to maintain engine RPM. In this case, the governor is going to vary how much fluid comes from this pump and goes into the motor. So the pump, it's going to have to accept that variable RPM from the engine. But the hydraulic motor is going to have a nice steady RPM, because the governor is going to make sure that whatever RPM it's at, it's going to, if it starts going too slow, it'll allow more hydraulic fluid to go in. If it's going too fast, it'll allow less. Of course, the fluid's going to come back to the pump, and it's going to go round and round and round. So constant speed drive essentially is a miniature self-contained hydraulic system that accepts a variable RPM from the engine, but keeps the generator, the AC generator, spinning at that one steady RPM. Now, every now and then the constant speed drive gets hot, or maybe it runs out of fluid, it leaks or something goes wrong. You don't want to damage the accessory section of the engine, because that's going to get really expensive, and it might damage the engine in flight. You really don't want to shut the engine down in flight. So what you're going to end up doing is have the ability to disconnect the constant speed drive. So here's the top of that big jet engine, and here's the accessory section. And in that accessory section is going to be a gear. And coming out of the constant speed drive, there's a gear that goes in here, and they mesh. So the engine is rotating, this gear spins, that gear spins, and this gear ends up spinning the hydraulic pump. But if something goes wrong with the CSD, this shaft in here, if let's say for instance the hydraulic pump seizes because it got too hot or it ran out of hydraulic fluid and had too much friction and it slowed down, then this shaft and this gear could bust up the gears inside of the accessory section. So on the side of the CSD is what's called a solenoid. A solenoid is just an electric, it's just a coil, and it's hooked onto a piece of metal. And I'm not doing a very good drawing it here, but if we pull on it, it's going to retract this gear back into the accessory section. So the constant speed drive will slow down, but the accessory section is unaffected. So this is a disconnection. This is a physical disconnection. Physical disconnection of the constant speed drive from the engine. Now, the engine keeps spinning around and around and around. The constant speed drive is going to slow down to 0 RPM. If we tried to shove this gear back in here with these gear teeth spinning around like crazy and these gear teeth from the constant speed drive being at 0 RPM, the gear teeth are going to break off and fall down to the bottom of the accessory section. That's going to cause a light to come on in the cockpit saying that you got metal in your accessory section. It's called a magnetic chip detector. So you're going to get a red light in the cockpit, and you're going to go, oh no, I got to shut down my engine. And since the gear teeth all got busted off anyway, the constant speed drive isn't going to work. So they've rigged it, engineers have rigged it, so that even if you flip the switch back to de-energize the solenoid, it still won't go back into the accessory section. You actually have to land the airplane, shut the engine down, wait till the engine has 0 RPM, and you have to open up the cowling, stick a screwdriver in there to push it back and re-engage it, and you cannot do that in flight. And there's a picture of a constant speed drive, and of course it's there to maintain the frequency of the generator by maintaining a steady RPM. And watch out, the constant speed drive is there to control the frequency, and the voltage regulator is there to maintain a constant voltage. So it maintains a constant voltage by messing with the amps, by changing the amp output, and the constant speed drive maintains a frequency by messing with or maintaining the engine RPM. So be careful. Voltage regulator is going to be working identically in an AC circuit, in an AC generator, in an AC system, just like it does in a DC system. It's going to keep the voltage constant by varying the amp output. Constant speed drive, it's going to be completely in charge of maintaining that 400 hertz, that frequency in the system, and it's going to do it by keeping a constant or keeping a steady engine RPM. And here's a picture of a big old honking jet engine. Here is an accessory section, which it's hard to see. There's more of it than that. And down here is the constant speed drive, and here is an AC generator bolted onto it. So the accessory section drives the constant speed drive. Constant speed drive drives the three-phase AC generator. Here's another picture of another jet engine. This is an old one. I'm not sure what engine it is, but here is the accessory section. This is being driven by the engine. The accessory section drives the constant speed drive, and the constant speed drive spins the AC generator. So it's very common that these are very large accessories bolted onto the engine. And of course, it's pretty easy to find because you can see the bunch of wires, big old honking wires, coming out of the AC generator. An integrated drive generator is just the CSD and the AC generator in one unit. So if we had a jet engine, see how fast I can draw a jet engine, and we took a shaft off of the jet engine and ran the accessory section, we'd have the integrated drive generator, but effectively inside of it we'd have the CSD and we have an AC generator. Essentially the only thing that's different is that there's a fluid system cruising around in here that keep cruising around, a cooling system that keeps both the CSD cool and the AC generator cool. That's an issue because both of these have friction, and temperature is an issue. Although they're energy conversion, well, the AC generator is certainly an energy conversion device, it's not 100% efficient. So some of the power coming from the CSD doesn't go out as electrical power. Some of it comes out in the generator as heat. And of course the CSD, we all know hydraulics, the hydraulic pump and the actuator in a CSD, essentially the hydraulic motor is a rotary actuator. We're going to have some heat. So having a cooling system is a good idea. You could blow air across it, but in an IDG they typically have a liquid cooling system. But electrically speaking, a constant speed drive and an AC generator are the same thing. And there's a picture. You can see the wire attachments for the generator, and here's where you add fluid to put into the CSDs on this side and the generators on that side. But it's one chunk. You can't take both parts out of it separately. You got to take the whole IDG out of the airplane if it needs to be replaced. GCU stands for Generator Control Unit, and there are several components in it. Voltage regulator. Whoops. So here's our AC generator, and here's our field winding, and here's our three outputs. So we're going to run these three outputs into our generator control unit. And of course we're going to end up hooking it up to 3 bus bars. First thing we're going to have, let's see if I can remember them all, is we're going to have a voltage regulator. So inside of here we're going to have a voltage regulator. You notice one side of it goes to the field, and of course the voltage regulator is also going to have to be measuring bus bar output, so it's going to have a wire, and we'll show it coming out here. We're going to have, of course, 3 bus bars because we're going to keep these 3 phases separate. There, that's the GCU right there. We're going to have 3 bus bars so that each of the three phases are kept separately. Voltage regulator is going to be connected to at least one of them to measure it, and of course it's got to be connected to ground so it can measure that voltage, and then it can decide how much power goes through that field. Oops. No, there's an L in there somewhere. Okay, let's see how many of these I can remember. All right, we've got the power coming out of the generator. We're going to run these through circuit breakers. And we're going to connect them. We're going to connect them so they all pop together or they don't pop together. So if any one of these output windings, if the amps in any one of them goes, it'll pull all three circuit breakers simultaneously. We're also going to have, so we're going to have a circuit breaker. We're also going to have, whoops, we're going to have, whoops, can't even draw. We're going to have a relay. You're going, Mr. Johnson, that looks like 3 relays. Well, you're absolutely correct. So I'm putting these dotted lines together. This relay is going to be connected so that when you energize one coil, all 3 of these, this dotted line means they're physically connected but not electrically connected. So it's going to close all of these at the same time to connect the generator to the bus bar. Now this is just a relay in here, and of course we're going to have some kind of a switch in the cockpit to remotely and electrically open and close a circuit. In this case it's going to be 3 circuits. But we can open and close this all day long. If we decide we don't want the generator hooked up to the bus bars, we can connect it or disconnect it all day long. Let's see. Oh yeah, and we're going to have somewhere in here, we're going to have a shunt. And whatever the voltage in one is, it's going to be the same in the other. So we're going to end up having a shunt out here so we can have some kind of an ammeter. So circuit breaker, voltage regulator, relay, and a shunt are the 4 things that we're going to have inside of a generator control unit. Now let's see if I remember them all. Voltage regulator, circuit breaker. Oh, there's a nice picture. There's a circuit breaker. You can see this one says 35 amps, but if we turn it over, ta-da, you'll notice that there's 3 connections: power in, power out, power in, power out, power in, power out. So one circuit breaker is going to, if any one of them need to be popped, it's going to pop all 3 of them. Relay, got that one. Shunt, got that one. Okay, and I wanted to make sure I talked about this right here. Disconnecting the CSD from the accessory section, once you've flipped that switch, even if you flip it back, it'll never reconnect in flight. That solenoid is not going, you can't energize it in the opposite direction. You can't make it get physically reconnected. But shutting off the generator to the bus all day long, you can open and close, you can connect and reconnect electrically. You can connect and reconnect the generator to the bus bars all day long, but physically disconnecting it, you can only disconnect it and then you're done. You don't get to use it for the rest of the day. Here is an overhead panel for an A320, and I know it's really hard to see in this picture, but here's the electrical portion. And if we look at a close-up, drive disc, this is the CSD inside of the integrated drive generator. They actually have a cover over it, and I know it's probably hard to see in here, but there's actually copper wire. It's a really, really thin copper wire, and you can grab on this and pull, and that copper wire will break. But you don't accidentally just open this up and push the button. Why? Because if you disconnect, that's what this says, is if you disconnect the CSD from the engine accessory section, you're not going to be able to reconnect it in flight, and that means you will not be able to use that generator the rest of the flight. VSCF stands for variable speed, constant frequency. Let's see, I'm gonna, whoops, won't do that. Draw you a picture. So we got our jet engine. It's got a shaft inside. We're going to take power off of it. Again, to run our accessory section, I'm going to draw this not to scale. So here's our VSCF. VSCF, it's not that, it's actually smaller than the accessory section. But we're going to take power out of it, and we're going to drive a DC generator. DC generator, wow, if it says generator, that means it's self-exciting. We don't need to get it excited. And it's going to have power, and it's going to run an inverter. And that inverter is going to change the direct current coming out of the generator into 3-phase AC. And it's also going to have a step-up transformer in there. It's going to increase the voltage. But I'd be happy if you realized that a variable speed constant frequency, it's got a DC generator. Of course, it's going to have a voltage regulator hooked onto it. And it can receive variable RPMs from the engine, but it's going to put out a constant voltage. And the inverter is going to kick that voltage up, and the inverter is going to change it from DC to AC. And it's going to produce that 3 phases of alternating current 120 degrees apart, just like if it was an AC generator. The good side is here, look, we have one moving part, the DC generator. This inverter right here is solid state. That is, it's got integrated circuits. That is, it doesn't have any moving parts. So one of the two advantages is reliability, because it has less moving parts. And the number 2 is accuracy. Accuracy in particular of the frequency, because this is computer controlled. If you had a gauge and you were reading the hertz, it'd be right smack on 400.0. It's so good. So there are some airplanes that don't have IDGs, or they don't have constant speed drives with AC generators. They have VSCFs. I know there is a model of 737 at a minimum that you can, I don't know if it's an option or with standard equipment, but you can get a variable speed constant frequency device on it instead of a CSD and instead of an alternating current generator. But it's still doing the same thing for us, producing a lot of amps and volts and 3 phases and in alternating current. Cool, man, this is my favorite part. Okay, I'm just kidding. I personally like the AC generators. All right, opposition of current flow in an AC circuit. You've already heard this definition here. That's impedance. Wow, if it's total opposition of current flow in an AC circuit, that's impedance. The symbol for impedance is Z, and it takes into account 3 factors. It takes into account resistance, which is one of the things the only thing you got to worry about in a DC circuit. Takes into account capacitive reactance, and of course XL, inductive reactance. You got to take all 3 of these into account. And of course XC and XL, we know about those. XC, the factors that affect it, it's the formula is 2 times pi times F times the size of the capacitor. It's varied by frequency, and it's affected by capacitance. And XL equals 2 times pi times F times L. It also is affected by frequency, and it's affected by the size of the inductor. So there's a really fast review. So we haven't talked about this one yet. Ohm's law in an AC circuit. And a DC circuit is pretty easy. It's just volts over current flow times resistance. But in a DC circuit, all we have to worry about is resistance. If it's an AC circuit, we have to worry about impedance. So it's going to be E over IZ. You got that? Ohm's law in an AC circuit is E over IZ. So now we're going to have to take into account resistance, capacitive reactance, and inductive reactance. And of course, both of these are affected by the frequency. And here's a fun graph. I want to see. Okay, maybe it's just me. I think it's fun. I recommend you draw this. Okay, this graph right down here is talking about frequency along this axis. And here we have ohms. And if we remember the formula for XL equals 2 times pi times F times L, if frequency gets bigger, then XL gets bigger. So if frequency gets bigger, then XL gets bigger, so this must be XL. And of course XC is the reciprocal of 2 times pi times the frequency times capacitance. So if frequency gets bigger in this formula, XC gets smaller. So this line coming down here, this must be XC. Now you'll notice that there is an intersection of XC and XL at a certain frequency. At a certain frequency, XL equals XC. And that frequency right there would be the resonant frequency. The resonant frequency has several characteristics, and one of them is it's where XL equals XC. In an airplane, helicopter circuit that's alternating current, in an alternating current system, we are going to have that resonant circuit at 400 hertz. The engineers all know, hey, we're going to run things at 400 hertz, so they're going to design components to work well and have low values of XL and XC at 400 hertz. So, I wonder what would happen if we weren't at 400 hertz. Let's just say we're at a higher frequency. If we're at a higher frequency, XC is lower and XL is higher. So when we were at the resonant frequency, XL equaled XC. In that case, at that resonant frequency, Z equaling the square root of R squared plus XC minus XL squared. This value right here was 0. They canceled each other out. So effectively, Z equaled R. So Z is at its lowest. A resonant frequency, Z is at its lowest. Well, if we look at Ohm's law, you got to remember, voltage is going to be held, whoops, accidentally hit something. Voltage is going to be held relatively constant by the voltage regulator. Remember, the frequency and the voltage and the amp output. The frequency and the voltage are maintained separately. So if voltage is held constant by the voltage regulator by varying the amps, and Z is really low, then I is going to be able to be nice and high. However, if XL and XC, if there is a large difference between the two, let's look at the difference between the two. Instead of the difference being 0, the difference is great. Now what's going to happen, this number right here is going to be greater than 0. Just for fun, we'll say this XC is 3 and this XL is 7. So if we plug the numbers in, 3 minus 7 squared, that's minus 4. But that's squared, minus 4 squared is 16. So now it's not 0 anymore. Now it's 16. So what happened to the value of Z? Z went up. So if the frequency goes too high, then the value of Z, or impedance, is going to go up. Well, if we have a constant voltage and impedance goes up, that is, the opposition of current flow gets worse, then current flow, more opposition, less current. So if impedance goes up, then amps is going to go down. Well, you probably don't remember this formula, but power equals amps times volts. Watts equals I times E. Well, E is constant. Voltage is held constant by our voltage regulator. If current flow goes down and voltage is constant, then power is going to go down. Wow, watts or power is going to go down. If power goes down, then two things are going to occur. One of them is our components won't work well. Or our components won't work at all. They'll either work lousy or they'll stop working completely. So we have an issue if the frequency goes too high. Now, really fast, what if the frequency goes too low? Let's see, I need another funky color. Let's say the frequency goes down here. Let's say we have a low frequency. Dun, 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 dun. Oh, now XL is low. And of course this is XC. So now this is XC. XC equals 7, XL equals 3. We come back over to this formula. Now it's 7 minus 3 squared. Wow, 7 minus 3 is 4. Wow, 4 squared equals negative 4 squared. So the value of Z goes up because now XC minus XL is now greater than 0, so Z still goes up. Well, if the frequency goes down now, I guess I could put it like this. If frequency went too high. But also, and if frequency goes down, we still have a big difference between XL and XC, so the difference here is still great. Z goes up, so Z still goes up. If Z goes up, and we have a constant voltage, Z goes up, opposition of current flow goes up, current flow is reduced. So current flow also goes down. If current flow goes down, we've got P equals I times E. E is held constant by the voltage regulator. I is going down, so now P is going to go down, or watts are going to go down. Wow, if watts go down, our components won't work well, or our components won't work at all. So hopefully this makes it abundantly clear that if the frequency goes too high, we're going to have issues. If the frequency goes too low, we're going to have the exact same issues. Less power at our components is going to occur because of less wattage, because impedance is going to go up whether the frequency goes up or whether the frequency goes down. We're still going to have these things occurring. So, hopefully, I've answered that question. Okay, let's talk a little bit more about power. We're concerned about getting enough power to our components. One of the issues with alternating current generators is XC and XL, and you probably don't remember very well, but if XC and XL don't cancel each other out, then they're going to push the volts and the amps so they don't rise completely. What we would like to have would be the volts going up and down, and have the amps going up and down and crossing at the exact same place. Well, P equals I times E. In this case right here, we'd have positive volts and positive amps. So if this is a multiplication, power is plus times a plus is going to be a plus. Here we're going to have a plus and a plus. Plus times plus is plus. Here we're going to have a negative times a negative, but negative times negative. Negative times a negative is still going to be a plus. So right here at this point in time, on this graph right here, negative times negative is going to be a plus. Here we have negative and negative. Negative times negative is going to be a plus. So here we have all positive power. But that's based on the volts and the amps rising and following and being 100% in phase. Another way to describe this would be no phase shift at all. And then a third way to describe this would be 0 degrees of phase shift. So this would be perfectly optimum. The problem is in airplanes, they're going to be out of phase at least a little tiny bit. So we got to take this into account. True power is taking into account the fact, well, I'll get to that in a second. True power is calibrated in watts. The K here is for kilo, which means multiply by 1,000. So 1 kilowatt equals 1,000 watts. On a Boeing 777, well, I'll get to that here shortly. Power factor. Power factor is directly related to how far out of phase it is. If we have the volts and the amps and they're not rising together, here, let's try it, not rising together. Here's volts, and this right here is amps. Right here we have plus volts, but we have minus amps. Plus times minus is a minus. Here we have plus volts and plus amps will have a plus. Here we have plus amps but minus volts, plus times minus is a minus, and here we have minus volts, minus amps. Minus times minus is a plus. If we added all these answers together, we'd end up getting 0 if they were out of phase by 90 degrees. A 90-degree phase shift is the worst case scenario. A 90-degree phase shift is going to give us no power occurring at all. Now, we're not going to calculate the power factor, but power factor can be anywhere from 0.0 to 1.0. A 90-degree phase shift is going to give us a 0 power factor. If we were 100% in phase, or a 0-degree phase shift, with the volts and the amps both rising and falling at the exact same point, this would give us a power factor of 1.0. Here we're going to have a power factor of 0.0. Airplane circuits are always out of phase a little bit. Airplane circuits are going to be out of phase just a little tiny bit. They're going to be out of phase 1 to 2 degrees. Or you could say they have a 1 to 2 degree phase shift. This right here is going to give us a power factor of 0.95. Or you could say it's 95% efficient. That is what a typical phase shift is in an aircraft circuit, is 1 to 2 degrees. That's going to give us a power factor of 0.95, because let's look right here. Right at this moment right here, we have a slightly amps are negative and voltage is positive. But most of the time, positive and positive, positive and positive, negative and negative, negative and negative. But right here, we have one positive and this one negative. So a little bit of the time, all of that added together would be about 5% of the time. So airplanes are pretty good, they're just not perfect. So the power factor is going to have to be taken into account. So true power true, equals, you got to remember, P equals I times E. True power is I times E times the power factor. So now we're going to take into account the phase shift. If the phase shift was 0, the power factor would be 1. So this would work out really well. True power would be really high. However, since we're going to have a phase shift, then it's not going to be always that 100%. Apparent power, we'll call that apparent power, equals I times E, period. It doesn't have the power factor in it. So if we have a phase shift greater than 0, we're not, and all we do is multiply I times E, then it's not going to be accurate. It's going to be what it looks like. If we just had a voltmeter and we just had an ammeter and we multiplied these two together to try to get power, try to get watts, then it would be inaccurate if the phase shift was anything greater than 0, if the power factor was anything less than 1. So understanding the difference between apparent power and true power is a really good idea if you're going to be a pilot flying an aircraft with alternating current power. Hey, that's large turboprops, large turbine helicopters, large business jets, and transport category jets. Because apparent power is going to be what a voltmeter and an ammeter might be displaying, but true power is what you really need to know. True power is always going to be a little bit less than apparent power because we're always going to have a little bit of a phase shift. So typical phase shift is 1 to 2 degrees. Typical power factor is 0.95. If you were flying a Boeing 727 and you were the flight engineer, you're essentially the computer that's operating the systems. There's going to be a gauge, the power gauge. And let's say you're flying along and let's say it reads 100 volt amps. That's probably 100 kilovolt amps. It's probably not that high. The Boeing 777 only has 90 kilovolt amps. But I'm going to use these numbers to make it easy. And there's a button right next to it. right next to this gauge. You're flying along, reading your magazines. Every now and then you put your magazines down and you look at all the gauges for all your generators, your AC generators, and you're going to push this button in. When you push the button in, the needle's going to come down a little bit. Hopefully, it'll come down to 95 kilovolt, 95 in this case. It's 95 kilowatts. That's true power. And what it's reading most of the time is apparent power. And what you want is this 5% difference. If there's a 5% difference, that means you have a power factor of 0.95 or 0.95, and that's pretty normal. Let's say you're flying along and you push the button in, and instead of seeing it go down a little bit, let's say you see it come down here to 70 kilowatts of true power. Wow, that means you have a power factor of not 0.95 anymore. You have a power factor of 0.7. The circuit is only 70% efficient, and something's causing it. Well, if a phase shift is directly messed up, or it gets worse because of frequency, then that frequency, you'll notice that frequency is also related to XC and XL, and both of them are affected by frequency. So what you're going to do, as soon as you look at this and you see that the phase shift is that the difference between true power and apparent power is greater than that 5%, the very next gauge you're going to look at is you're going to look at the frequency gauge. And if here's the green arc, oh, I could draw a green arc. Cool, man. If here's the green arc, and right smack in the middle of it is 400 hertz, then my guess is if you have this there's probably a red line right here and a red line right there. If you have this significantly greater than 5% difference, it probably means that the frequency is either too high or the frequency is too low. Now the good news is, on this airplane, there's a knob right next to it. We're talking Boeing 727 where the flight engineer gets to do it. This knob, you can rotate it left and right, and this actually controls the CSD governor. And as you rotate this knob, it tells the governor to spin faster or spin slower, and you can actually bring the frequency back to where it's supposed to be. You can actually bring the frequency back to 400 hertz, and I bet you $10 if you bring the frequency back to 400 hertz, when you push this button in, instead of the needle going down 70%, it'll only go down 5%. And just so you know, apparent power is in volt amps, and of course K is for kilo. I've also seen it volt amps reactive. So your gauge might say kilowatts and kilovolt amps, or it might say kilowatts and kilovolt amps reactive, but it still means the same thing. Whoops, I messed that one up. Kilovolt amps, there we go. So kilovolt amps and kilovolt amps reactive are the same. And of course we cover the typical phase shift, and if the volts and amps are way out of phase, then we're going to have a power factor of less than 0.95. And of course, guess what? Because our frequency is going to be too high or too low, that's also going to make our components either not work well or they won't work at all. So power meter, I got a picture of one. Wow, dig it. Kilowatts or kilovolt amps reactive. So there's an example of one. And of course, what's the purpose? Same as any other meter or a hydraulic pressure gauge, tells the pilot an indication of system condition. In this case, it's going to tell us apparent power versus true power. And now for the simple AC power generation circuit. We'll see how well I can draw pictures today. Let's put a nice big old bus bar up here, and it's probably going to be 128/208 volts DC. Now I got to tell you, when I'm going to back up here. Remember, I drew the AC generator, and we had it going into the generator control unit, and it was going to come out and go into 3 separate bus bars. In reality, that's what it looks like. You have 3 phases, 1, 2, and 3. But drawing it on diagrams, they don't tend to draw diagrams with all 3 of these. So on a diagram, a schematic, we're just going to draw it so you get used to it, that there's just one. So although we're going to draw one bus bar, we know that this is 3-phase, even though we're only going to draw one. So going into it, we're going to have a generator control unit, and before that is going to be our AC generator, and driving that is going to be our constant speed drive, and of course that is going to be hooked on to our engine accessory section. And we need our solenoid, so we can disconnect it if we need to. We're probably going to have a temperature gauge on the constant speed drive to tell us if it's getting too hot. In fact, we're probably going to have a hydraulic quantity gauge. We might have a temperature gauge on the generator, and of course coming off of the generator control unit, and we might have a voltmeter, we might have a power meter, and we're always for sure going to have a frequency meter. And then of course we can run motors, and we can run light bulbs, and all kinds of things. And of course you'll notice I'm not drawing all the 3 wires, but in reality there's really 3 wires going here. So in an AC power generation circuit, we're going to have the engine accessory section driving the constant speed drive, accepting a variable RPM and spinning the AC generator at that one steady RPM it needs to spin at the right frequency. To spin at the right RPM to deliver the right frequency, we're going to have that voltage regulator. Of course, it's going to be connected to bus bar, and it's going to be connected to ground, and of course it's going to be connected to the field winding in the generator, and of course we're going to have all that other stuff inside of the GCU, which I'm not going to cover again. So it's very similar to a DC power generation circuit, except that frequency is now a really big deal. So we got to handle that, and so therefore we've got this whole mess here with the constant speed drive we got to deal with. We got frequency, power is going to be affected by it, but voltage regulator is going to be the same. We're still going to feed the bus bar. It doesn't show it, but here, here's the ground to the AC generator, so it's still going to have to be grounded. And a voltmeter doesn't show it very well, but the voltmeter is going to have to be grounded. I'm not going to worry about putting the grounds in. So now, if we stop worrying about frequency for just a minute, then maybe we can realize that, wow, we got to take power off of the engine. We got to control the output. In this case, not only control the amps to maintain voltage, but we got to control the RPMs to maintain frequency. But hey, we can turn stuff on, turn stuff off. You'll notice there's no battery. Batteries don't get hooked up into AC systems. So we probably aren't going to try to turn everything on at once or turn everything off at once, because we can't have the voltage be slightly smoothed out when we turn lots of things on and off. But except for having a battery out here, which we don't have, we can have a power system extremely similar to a DC power system. You know about the connections, any questions, improvements, you know how to get a hold of me. Thank you very much.